Hello and welcome everyone. This is Peter Robinson and this is the Ethereum Engineering Group meetup. So today I've got Bao Cheng with me, who is going to talk about tools in blockchain development. And so Bao Cheng, before you start sharing your slides, why don't you please introduce yourself?
Kiddo, thanks, Dr. Robinson. And I'm going to briefly introduce myself. So hello, everyone. My name is Bao Cheng Wang, and I'm currently an undergraduate student in the University of Sydney, Australia. And I'm doing software engineering for my major. So I'm in my final year. So I'm doing an honors project with my supervisor, Dr. Shiping Chen. And what I'm going to share with you guys today is actually part of the research that I've been doing for my honors project. And should I just share the screen?
Yeah, and so I asked you before, but just so everyone else knows, so for questions, put them into the chat and then we'll go through them at the end. So Bao Cheng wanted to do his talk and then do questions at the end. But yeah, so please, yeah, do share your slide.
Okay. So I've shared it. Can you guys see it?
Yes.
Okay, I'm gonna start right now. Okay, so the topic of my presentation is the evaluation of contemporary smart contract verification tools. So, and this agenda we're gonna cover today. And the first thing I'd like to talk about is actually the motivation of our project. What drove us to do the project? It's actually a pretty simple question, like, is smart contract actually safe? Because it's pretty vague. Like people have been introducing about blockchain, and safety, security, transparency is kind of like the very first keyword they use to introduce the blockchain smart contract. So, and after the rapid development of smart contract, and we now have thousands of decentralized application, which accumulate huge financial values. And especially when we consider about the feature of smart contract, once it's deployed on the blockchains, cannot be updated anymore. So, which makes it somehow dangerous. Especially, I'm going to introduce a few well-known incidents in the history of smart contract that can demonstrate smart contract is not exactly safe. Well, the very first incident I'd like to talk about is the DAO attack in 2016. I think it's the most representative one and most well-known one. Well, the attackers is find out there's a vulnerability, re-entrance vulnerability inside the DAO contract, and then drain the contract and steal around 60 million US dollars from it. And in 2017, we have a multi-sig parity wallet hack, which caused an embezzle of around 30 million US dollars, and around over hundreds of accounts was frozen due to the hack. And then we have a BEC token attack in 2018, and which caused a financial loss of around 900 million US dollar. Which is the most interesting thing is just like a few days ago, we have another well-known hack. It's called a BNB chain bridge hack, which costs around 570 million US dollars. So from all the incidents, we can learn that smart contract is not 100% safe. And as a developers or the stakeholders of smart contract, we have to make sure this before we deploy it, it can reach some conics of security. So I'm then gonna do some scope definition for the project. So what we are focusing on the smart contract verification tools, and we only care about the smart contract that is deployed on the Ethereum blockchain and that is written in the Solidity programming languages. And we all know, like, sometimes the verification tools takes in the Solidity source code as input, or sometimes the EVM bytecode. And in our scope definition, we only care about this verification tools that takes in the source code. And the most important thing is, like, when we talk about attacks, we only care about the attacks that is exploiting the vulnerability within the contract only, because we have a variety of attacks, such as we have a denial of service attack, which is attacking against the network. And we have a 51% attacks attacking against the blockchain. Those are definitely out of scope. And before we talk about the experiment, we have to admit some limitation of the study. First of all, we will, for the fairness of the experiment, we will not fine-tune the tools in the experiment, which means we'll only use the default parameter settings, because a few of the tools allows the user to customize its performance by setting the parameters in the command line. And therefore, at the same tool with parameters fine-tuned by professions is likely to achieve a much better performance than the evaluated performance in the experiment. Then we talk a little bit about methodology. We can just divide our research into 4 stages. The first stage is a preparation stage, where we select some representative verification tools and smart contracts. And in the experiment stage, we just scan the benchmark, which is a simple smart contract we selected in the first stage with those verification tools, and collect the result or the data. And in the evaluation stage, we do the comparison of the data, and we make some evaluation and make some observation based on the evaluation. And at the last stage, we propose to make some improvement based on the existing tools. So to select those verification tools, like after we have done some research, there were like over 20 smart contract verification tools that is commonly used on the market. And like listed below, it's in the leaf notes. And definitely we don't have enough time to experiment on all of them. So we have designed a selection criteria and select 3 of them. The selection criteria is actually have 5 factors. The verification tools should have an active ecology, like has a constant update or releases. And we prefer vulnerability detection rather than formal verification, as derived from the our motivation, just mentioned before. And the third point is like the verification tools should support some up-to-date Solidity version. It doesn't have to be the latest Solidity versions. For example, when I was doing the research, the latest Solidity version was like 0.8. It doesn't have to be exactly 0.8. I'd say there should be no less than 0.5 or 0.6. And also, just like mentioned before, the verification tool should take in the Solidity source code as input. And the last one is we prefer the open source project or the free one instead of the closed source one. And the 3 tools that we selected out was the Maestro, Listen, and Securify. And some information was summarized in the table here, especially the version that will be used for the experiment. And the open source license is also listed. Just so you guys know, like the start in the Solidity version column refers to the wildcard. It basically means it supports all the Solidity version that is available online. And then we talk about the benchmarks, the selection. We also design a selection criteria based on it. And first of all, the smart contract should be written in Solidity, and the Solidity version should be in the range of 0.5.1 and 0.6.8. And most important things, like since we're doing the evaluation, we should make sure we want to know how many vulnerability are there and what kind of vulnerability are there in the contract. So we will need some trusted third-party verification results that can be used for reference. And the ideal references was like a previous auditing report or inspection report that is generated by some professional inspection team. And while the benchmark we just selected out was 3 real-life DeFi project, the Uniswap, PancakeSwap, and BTRST contracts, and also SWC registry. Well, it's quite different. It's not a D app. It's a collection of smart contracts, simple ones that is dedicated to demonstrate some particular defects and how to fix them, which is initially proposed by the Ethereum community and now maintained by the consensus, I think. And there's some information about the benchmarks. I have used the commit ID on the GitHub to indicate the version I use for the experiment, and also the range of Solidity versions that is used in the smart contract. And also I have counted the total number of errors that it's confirmed to be existed in the smart contract based on the auditing report and the results of the verification tools. And this column simply refers to the smart contract did have some third-party inspection report. Then we talk about the design of the experiment. Like we have designed two groups of experiment for the project. The very first one is called baseline experiment. It's a qualitative experiment that measures or analyzes the reliability of these tools. Because we use these tools to examine 3 well-known attacks contract and determine if the exploited bugs could be correctly flagged. And the 3 well-known attack contracts can simply refer to the first 3 well-known incidents I just introduced in the motivation page. And the second group of experiment was called quantitative experiment, which measures the performance of these tools. And we have designed 3 evaluation matrices. The first one is the accuracy, which has 2 main indicators, the false positive rate and the false negative rate. And the second matrix called performance also has 2 indicators, the average execution time and timeouts. Those indicators are going to be explained in the later. And the third matrix is called robustness and going to be indicated by the times of failures. Then I'm going to show you some snapshot that I took when I was doing the analysis. The first page was when I was doing some verification, when I was analyzing some smart contract using Maestro. That's a command, and that's some vulnerability report generated by Maestro. It's a pretty detailed one. It demonstrates the some description and some severity, also some location that of the code in the contract, and some estimated gas usage, and etc. And this one is the vulnerability report generated by Securify. Well, the color is a little bit confusing because even though it's highlighted in red color, but the severity is actually low, so it's a little bit messy. And the last one is actually the report generated by Stelissa, and this is easy to understand. Then I'm gonna talk about the experimental data. The summary of the baseline experiment. Since it's a qualitative experiment, the outcome can simply refer to some true or false statement. Well, we have summarized it into the table here. If it's a tick, refers to the verification tool successfully found the exploited bugs in the attacked contract. For example, like the DAO contract, simply it refers to Maestro has detected the re-entrance vulnerability inside the contract. And the slash here refers to it fails to execute the program, mostly because the Securify does not support the Solidity version that is used in these 2 contracts. Well, to be fair, those are a little bit out of date, and I remember the DAO contract is using the Solidity compiler of the version 0.3, I think. It's definitely not supported by Securify. That's why it failed to execute. And as for the BEC token, well, none of those verification tools succeeded in finding the integer overflow vulnerability inside it. So that's why they're having a cross here. Then I'm going to show you some data. It's a table of the quantitative experiment. We have a lot of them. Don't worry, we're not going to talk about every of them. Mostly, I'm going to explain what the row means using this table, and I'm going to do the analysis using the summarized one. So on the first row is the number of errors. Majorly, it represents how many errors was reported by the verification tools when examining all the smart contracts in the column. For example, Maestro has reported 46 vulnerabilities when scanning all smart contracts in the established registry, and 9 of them was false positive. Simply means the false alarm. For example, it reported that line 9, the contract has a vulnerability, like a re-entrance vulnerability, but when we do the manual checking, we found the line of code was actually benign, doesn't have the vulnerability, then it would be counted as a false positive. And false negative is how many confirmed errors based on the audit reports was missed by Maestro. It's 79, and false positive rate is actually the false positive divided by the number of errors. False negative rate simply refers to the false negative divided by the total number confirmed errors that exist in the contract. And then we talk about the average execution time. Like we'll do the timing for each execution, and we'll repeat the execution for 4 times and do the calculate the average time. And that's how we computed the average execution time. As for the timeout, we actually set an upper bound of the timing of each execution. And the upper bound was like 120 seconds. Once the execution exceeds the 120 seconds, it will count it as one timeout. The failure was just like I talked in the baseline experiment. Sometimes during the execution of the verification tools, some issue might occur and crash the system, and it will be counted as a failure. Mostly it was caused by the unsupported Solidity version, just like Securify. And so I'm not going to show you the summarized table. I put it all together. Some key observation can be derived from it. Like Maestro is reporting far less errors than Solidity and Securify, and all the tool has a relatively high false negative rate, ranging from 47 to 81%. And as for the execution time, the performance, like Maestro is showing the least ideal performance as 42 seconds, while the others only takes less than 1 second or 2 seconds. And when it comes to the robustness, like Securify has 25 failures. Well, this is not good. And as for the accuracy, I have visualized the FPR rate, false positive rate, and false negative rate in the diagram here. Well, you can see Maestro is actually showing the least accuracy because it is having the highest false positive rate and highest false negative rate. And Solidity has the least false positive rate, while the Securify shows the least false negative rate. Then we have summarize the key observation. Well, Maestro, it's only demonstrated a few vulnerabilities, while 55 compared with 700 and around 1,000, which leads to the highest false positive rate and false negative rate. And we concluded in the low accuracy. And also it has a relatively long execution time. And it is worth noting that the execution time actually can be reduced by fine-tuning parameters. And yeah, and Maestro is the only one that supports integer arithmetic detection. So if we want to detect some integer overflow issues, Maestro is the only shot among the three of them. And when you consider about severity of those of the vulnerability reported, actually Maestro found the majority of the vulnerability reported by Maestro is actually a higher level of severity, like the high or medium level of severity. And then on the bright side, has a very good usability, like it has a detailed report and it has a high flexibility. Well, it allows user to customize the verification tools by setting multiple parameters. And when it comes to the Solidity, it reports a large number of vulnerabilities and lead to a high accuracy because that is the least false positive rate. And the execution time is the least because it's less than even 1 minute. And it is also worth noting that when we consider about severity level, the majority of the vulnerability reported by Solidity is actually on the info level. And those kind of vulnerability usually do not pose a threat on the security, but cannot be easily refuted. I'll give you an example. Like, for example, in your smart contract, there is a line of code, and where you are declaring a variable, and your variable naming is not actually following the Solidity naming convention, and Solidity would flag that the line of code and report the vulnerability of naming convention. Was actually debatable, like because it doesn't really pose a threat to security because the attackers cannot breach your smart contracts by exploiting your variable naming. But from the perspective of smart contract quality, if you the conformance of the naming convention can have some positive influence on the overall quality. So you cannot simply just deny the set it as a false positive. And when we talk about Securify, it's pretty much like Solisa. It has a large cardinality, which means it reports a huge amount of vulnerabilities in the lower severity, and it is extremely low in the false negative rate, because these vulnerabilities were missed by it, which can be explained because Securify supports most detectors compared with others, which means it can detect the most categories of vulnerabilities. And it also has a high performance due to the average execution time. However, the downside of the Securify is definitely the robustness, as it has 25 failure times. And after the evaluation stage, we will talk about some future things, like how we propose to improve the existing verification tools. Like we will first detect issues in the existing tools based on the evaluation. And our final purpose is always like to reduce the false positive rate and reduce the false negative rate. And in order to reduce the false positive rate, is actually we just need to optimize some existing detectors we have. But if you want to increase or optimize the false negative rate, we will have to develop much more developers. So develop much more detectors to widen the vulnerability coverage when it's doing the verification. So from my perspective, optimizing the FPR rates is actually false positive rate is a easier work. And so my initial attempts actually reducing the false positive rate by optimizing some certain detectors, which are causing the major source of the false positive. For example, the dangerous strict equality, arbitrary write access, or the transaction order. And yeah, that's all for today. And this reference I have been used for the to do the PowerPoint. And are there some future talks on the Ethereum engineering group? If you're interested, you can just interact with the engineering group, like via these URLs. And thanks for the listening. I'll check on the question. Also, I'm gonna stop on the on this slide.
Yeah, thank you. Thank you. So that was a great talk. Cheng, I've got so I asked people to put questions in, and I put a question into the chat there. So you compared the, the issues, but what about if you just look at those high impact issues, and how did the various tools compare? Like, did they all find the same high impact issues, or did some of them have false negatives for the high impact issues?
Well, it's kind of like the one limitation of our study, because when you are doing the experiments, actually it will just report the severity, but I didn't really take it down like in the data. When I wasn't really I didn't really notice the importance of the severity. So it's kind of like the limitation of the study. But when I was doing the experiment, I kind of hit I do remember like the seldom do the Solisa and Securify reported the vulnerability of the high severity. So it's, the shame is I didn't really get to record the data.
Yeah, I guess then you would also need to do an analysis of, does Securify decide that this thing is important compared to some other, the other tools. So Mithril might say this one's high severity, whereas say Slither might say it's low severity. So then you would have to try and work out what is high and low. Milad's put some questions in the chat there. Milad,
Okay.
do you want to walk through your questions, Milad?
Hello, everyone. Yes, I can do that. Can you hear me?
Okay. I'm still reading your question. Sorry.
No worries. So one question is, how do they compare against user friendliness? You're a software engineer trainee. And then I would say maybe you already have developed skills to deal with software, but what about an average user of these tools? How much difficulty do you think they would go through? That's one question. The other thing is, these are mostly vulnerability detection tools. They're not verification tools like theorem provers or other software like FStar or Daphne. I'm wondering why you have chosen to refer to them as verification tools instead. Thank you.
Okay, so for your first question, how do we compare like the user friendliness? It's actually well, from my perspective, it's more like a subjective issue. Like, because when you are doing the analysis, like you are keep operating with those tools, actually you will find sometimes the report is friendly, as user friendly because it's more detailed, and sometimes you can actually customize those kind of tools by setting the parameters. It's just make you feel more flexible, and yeah, just pretty much like it. So it's like as long as you just execute those or operate those, and well, it's more like subjectively, you will find the user friendliness. And I hope this answer your question. And for your second question, well, I'd like to answer based on this one. Because normally when we talk about the higher topic was actually smart contract verification. Like this, it's a root node was a smart contract verification. So it's kind of like I used to call all of them the smart contract verification tools, like refers to actually all of them. But as a subcategory was like can be divided into vulnerability detections or the formal verification. So I think you're referring to formal verification tools. But so what I was referring to is smart contract verification. So does that answer your question?
Thank you for your explanation. I'm mostly interested to see how you perceive things, and thanks for your description.
All right, thank you.
And so are there any other questions? No, looks like everyone's happy, which is good. So, well, thank you very much for your talk. And the fact that we've still got right to the end, we've got people still joining shows that it's a talk of interest, which is good. So thank you.
All right, thank you guys for listening.
Yeah. And if you were to share that slide just once more.
Oh, you mean the future talks?
Yeah, I was just going to quickly run through. So next week we're having a break, but in 2 weeks' time, Dr. Ermias, who's on this call, is going to deliver a talk on cross-chain security. And then the week after that, we've got the people from the ZK Bridge team are going to present their technology. And then 2 weeks after that, I'm going to do a talk, and it's going to be on ABI encoding. So how is data moved around and how is it encoded? What does that look like? We've got quite a few more talks on people presenting on their research topics, the DDAR and the blockchain disruptor for accounting. In mid-December, I've got another solidity test. And so people said my last solidity test wasn't hard enough. So I've got a new solidity test that I've put together. So we'll go through that live. So that'll be a live programming thing. And then we're going to have over winter or summer, depending on whether you're in the northern or southern hemispheres, we're going to have a break of a few weeks. And we're coming back on the 18th of January. And so we're going to have Ben Edgington come along. So that's actually going to be 6 p.m. Brisbane. So better for people in Europe, not so good for people who live in Americas. And he's going to talk about the approach to sharding that is being worked on now. So execution shards. And so I know we've got roll-ups, but this is the step beyond that. And so that's going to happen. And then we've got a whole stack of talks lined up for next year too. So lots of things coming up. Yeah. So are there any final questions for Bao Cheng? before we leave it?
Yes, hello, Bocheng. This is Nihar Shayar, and I'm new to the blockchain space. If I ask this, how do I start my smart contract auditing journey from scratch?
From the macro scope,
Yeah,
would you like to? You mean the smart contract? You like to start developing smart contract or verifying smart contract? I care about the security or just developing them?
no, I know about the development of how to audit a smart contract.
Smart
Yes.
contract set. If you would like to audit smart contract, I suggest you
Yeah.
to learn a bit more about the smart contract verification tool, just mentioned before on the previous
Mhm.
page. Like even though like they cannot fully replace the auditing, it still can have inspiring on how you interpret those data, how you inspect them. Like I'm gonna show you this page. Well, because especially when you consider about them using different kind of technology or the methodology, like symbolic execution, fuzzing, abstract interpretation, like they're using different kind of technology. If you combine those, or just see the common things between those technology, it does have some inspiration on the auditing. But well, generally, I'm not doing I'm not a professional audit or inspector, I guess.
Yeah.
So
Nihar, what I could suggest as well that, so when you use a Solidity compiler, there are warning messages that come up. Have a look at them and make sure you don't have any warnings. I think that's a really simple starting point thing to do. We've done I did a security talk, Solidity Security, Smart Contract Security, about a month ago. Have a look at that talk. That might give you some ideas. And dare I say it, but just have someone who isn't yourself and maybe, you know, is not part of the team directly, just do a code review. And so simple things like comparing your architecture document with your code. Another area of interest is have a look at, so, you know, you've got your architecture document. Another thing you can do is called threat modeling. And so threat modeling is trying to look at your attack surfaces, so how someone could attack the system. And so if you Google threat modeling, that will probably help you as well. And so, you know, I think if you take a multi-pronged approach of having an architecture, doing threat modeling, having a code review, then that would put you in a good place for some external audit.
Sure. Thank you so much. I just joined this group today, so thank you so much for that, and thank you for the suggestion. I'll definitely look forward for the video.
thank you. So listen to Dr. Robinson. It's much more insightful suggestion.
Oh no, I think using a variety of tools is a good idea too, because they will find different things. So yeah. And are there any other final questions?
One quick question. Have you looked at other tools like Oyente and some other vulnerability detection tools?
Yeah, actually, I have investigated a few of them, and Orient is kind of like the very first tool that I investigated, because that's one of the very first verification tools, isn't it? Like, but actually, I thought based on my selection criteria, like the Solidity version is should be around like in the range of this one, but Orient is like doesn't really have a constant update. So I remember the last release of the Orient was in 2017, and so the latest Solidity version supported by Orient was like 0.4, I think. So pretty much, basically all the smart contract I chose can all be verified by Orient. That's why I didn't really choose it. I'm sorry, does that answer your question? Because I'm a little bit...
Yes, thank you.
So, I mean, we're up to 0.8. Do you, any of the tools that you've talked about today, do you think they are being actively maintained? You know, like if you were to look at the GitHub repo for the actual tool, are there recent commits to the repo, or have they all sort of fallen by the wayside?
I would say Maestro and Solisa, like they have a very active ecology. Like they all have the latest commit was like just a few days ago, or there was a time that I found the latest commit was just like an hour ago. So they definitely have someone is, oh yes, Solisa has a community behind it. And I think Maestro is actually maintained by consensus. So they both have been constantly maintained, but I have consulted some professions. Securify is kind of like academics for the academic purpose. So it tests about the ecology is less active compared to those two.
Yeah, I think that that's something that's important because, you know, the language changes, you know, the Solidity language changes with time. And so if it can't analyze new code, then it's a real problem. Yeah.
This is inspiring.
Yeah. All right, I'm going to do it one more time. Are there any more questions?
It's really like the auction, like we have to keep
Going. Well, one person once said that you should wait 40 seconds to see and have 40 seconds of silence, and then you'll know that there really are no more questions. But look, thank you for doing a fantastic talk today, and yeah, have a great day. And I'll post the recording onto YouTube probably later this afternoon. So thank you again.
No worry, yeah. I cheers, mate.
Yeah, thank you. Bye-bye.
See ya. Still sharing.
Bye-bye.
See you guys.
Well done.
I thank you, Professor.